สรุปจากตัวแทนบริษัท Ultra RT Technology จำกัดนะคะขอ May I call on stage Mr. Binod Marco Asia Pacific Region for Ultra RT Technology to give us an introduction hardware interlude.
Saudi Cup. Sorry, cannot speak that. So only Saudi Cup, Captain Cup, Noy, Macmac.
I know that it's very late and everybody needs to go home. So
give me 10 minutes, I'll go through my presentation quickly. And tonight, if you have nothing to do, you say, oh, what Ben say, and then you could check the presentation later, okay? Is the presentation ready? So, following the good presentation of Dr. Sugda, he was focusing on use of hardware in the loop for power system. Obviously, hardware in the loop is a very general term. We have customers in power system, in power electronics, and my presentation is focusing on electric vehicles and power electronics of electric vehicle. But the one thing you should remember is the purpose of hardware in the loop is to test a device in the laboratory so that when you install it in the field or you deliver to the customer, it's ready. Everything has to be tested in hardware in the loop. If you talk about power system, you talk about protection relay, you talk about controllers, you talk about, we have customers who are making air conditioner. They're testing the motor control of the air conditioner with hardware in the loop. Everything is tested with hardware in the loop. So we'll focus on the EV. Those of you who don't know APAL-RT, we're from Montreal, Canada. 25 years ago, 400 people, many customers. Here are some electric vehicle companies that are our customer. Obviously, in Thailand, we're working with our friends from PTS Combination. So if you talk about power electronics for converter, you have different types of topologies for trains. You could have multi-level converters. You have converters for vehicles. Sorry. Oh, young engineer. So good. So we're able to test electric vehicles in different configuration. Now we have more complex topologies that need to be tested. And here I will not be talking about our product. I will be giving examples how to use our product. If you have questions, you could ask them later. So in the world of automotive, there's 4 different categories. We could talk about charging, about propulsion, batteries, or ADAS a little bit. This was already covered by Professor Sugda. So if you talk about charging, there's 2 issues. There's the charger, which is the charging station between the power grid and the vehicle to be charged. So you have the charging station, and you have the onboard charger. This is the charger on the vehicle. If you are somebody who's working in the power system field, you are focusing on the impact of the charging station on the grid. If tomorrow morning Bangkok has 100,000 people driving Tesla car, every Tesla is 100 kilowatt, then you have 10 gigawatt of power that needs to be supplied to the charger. So this is a study for the friends of IGAT or MEA. If you're focusing on the vehicle itself, then you want to improve the charging power electronics device to improve efficiency. This is hardware in the loop. So you have here control of the device under test to control this. One example of this is a university in Toronto, Canada. They made a charger for trucks, and the focus was to the speed of the high frequency transformer on the active bridge to be able to do this. We have another customer in France, I think, Valeo. Probably you've never heard of Valeo, but it's actually a very big company. They supply parts, OEM to makers, and you can see that since 2016, they supply onboard charger to many types of vehicle. If you look at this, you have some BMW car, Volvo, Renault. They have e-motors also for different type of vehicles, inverters, and all those devices are tested using the Opal RT system. In the case of Valeo, the big technical challenge was for the DC-DC converter. On the AC-DC side, they were using switching frequency of 80 kilohertz. Those of you who are expert in that field, 80 kilohertz starts to be a challenge in terms of simulation. Only Opal RT can do it. However, the big challenge here was for the DC-DC converter, where they're working at 400 kilohertz, and they're very happy working with us. We're the only supplier who are able to help them test. So here, they're testing both the charger and the onboard charger to be able to provide this. So when you give to their customer, they know that the testing was good and the results are okay. This is an American company called Lucid. They're using our tools for testing their electric vehicle for the inverter and the motor control. If you talk about inverter, this is a very simple diagram of an electric vehicle. You have the device under test, which could either about the battery, the inverter, or the motor model. So in the case, this you could read later, it's not so important. Those are the type of motor we can do. When you focus on motors, very important, I'm sure you heard about FEA, finite element analysis motors. So when we use a classic DQ model, what we all learn, and you're all professors of university, so when you're university, we learn about the DQ model. So that motor model is actually a simplified version, where you have impedance in the D and Q axis. What happens is that in steady state, you have nice sine wave of the current when you're using the DQ model. If you're doing studies of power systems or general purpose, it's okay. If you are focusing on the motor model for an electric vehicle, this is not correct. You need to have finite element analysis models. Those models have actually think about the stator of the motor and the rotor turning inside. So actually what happens is that when your notch between the stator and the rotor are in front of it, your impedance value is changed because the rotor will go to the next notch. So that means between each notch, the impedance change. It's a 3D matrix. Your impedance will change based on the position of the rotor from 0 to 360 degrees, and repeat. And the impedance will change on the power. If you're working at 10 ampere or at 100 ampere, it's not the same impedance. So this means that in steady state, a real FEA motor has some harmonics on it. Now, you will say it's not so important, but I will have an argument against you. Customers like many years ago, Toyota, when they're making the Prius vehicle, they're focusing their IGBT firing for the electric model based on this waveform. So if you make your model and you're simulating a standard DQ model, that means that all the optimization you're doing does not reflect the real world. Hence, you need to have FEA models if you're doing high-level studies. Customers using our tool for a very simple air conditioner. You're thinking air conditioner, very easy. You have a compressor outside. But if your firing of the drive are not perfect and you're using the bad model, probably that you'll lose 10% of efficiency. So then if the competitors are doing it, you're losing money, you're losing business, you're losing efficiency. So anyway, just to say that this is very good. We also have customers. Professor Sugdai mentioned PHIL. HIL for hardware in the loop, PHIL for power hardware in the loop. So normally in a project, you will test your first controller offline. You're doing only simulation. Once your results are good, you go to the next step. You will have a real prototype, a real device, a real controller. Once this is good, because you're only testing it at 10 volts, then you want to go to power. So you want to test it at a real kilowatt. This is what we do here with our friends from DV Electronics. where we have our simulator connected to a big amplifier. This simulates we have a 1000 volt or 300, 400 ampere, where you're testing a real inverter. So here we're not only testing the inverter model or the inverter device, we're testing the real inverter. So this is another level of testing. Of course, if you're in university, it's maybe academic, but if you are a real manufacturer, this needs to be done eventually. So this is what we're able to achieve. Another issue is battery management system. I will say many times the word BMS for battery management system. So the whole purpose here is that electric vehicle needs batteries. You want to test the battery. We say the word battery, but actually the real battery in the vehicle, you have hundreds of small batteries, all connected in parallel. You take a Tesla, inside it they have, I think, 500 something small batteries. All those batteries have the temperature sensors to check if they're overheating or not. And all batteries need to be checked to make sure that one of them is not short-circuited or damaged or overheating. So you've got 500 temperature readings to measure, you've got 500 devices to check. So you need simulation tools to do it. We have that in our battery management system, where first you can do simulation of it, but eventually we will test the real battery. Now, you don't test a real battery, because if you test a real battery, this is dangerous. A real battery, if you short circuit, it could explode, it could catch on fire. So normally testing real battery, you need a fireproof room so that nobody dies. So what we do, we actually use battery emulators. So battery emulator simulates a battery function without any chemical problem, where you can study the voltage, current, temperature, fault of everything. So you simulate that, and then all the information from the battery emulator are sent to your BMS, so the device under test, to be able to reproduce it. The purpose is obviously to make it a better one. This is the detailed schematic of how it's working, because you think about the device under test and you think about the battery, but actually there's different kinds of sensors, of resistors, of breakout box, tools that are used to make short circuit between lines. Sometimes finding a short circuit is easy because no current, no voltage. But what about if you have a 90% short circuit, or 10%, small wires that are touching? So you need to be able to test that. It applies not only to electric vehicle, it applies to everything, but here I'm talking about this. This is different topologies, which you can read later tonight if you don't sleep. We have some example of BMS here. Hyperloop, I'm sure you've heard about this, making transportation in the tunnel. They're actually having BMS inside every pod, so they're using our system to do that. And Harley-Davidson, which is known for big motorcycle, they have electric version of that. So they're testing their electric motorcycle with our Hop-LRT system to do this. Harley-Davidson are popular for the big sound they make. I don't know if they have an electric vehicle, how that works, but that's another thing. I've got only a few minutes left because somebody's pushing me. So we talk about ADAS. So ADAS is a popular topic right now because it refers to autonomous driving. And autonomous driving obviously is hot. There's a lot of work to be done. We have some packages that are making available for people to do this. The main purpose with ADAS is that testing is difficult, because you cannot say, okay, I want to test my new algorithm for driving. You need to have thousands and thousands of test data so you can compare it. You have a soy and then a sumac passing, that's test number 1. Same soy, you have a sumac and have rain, that's test number 2. Same soy, have sumac, rain, and car coming another way. So you've got millions of tests if you're on the highway, if you're in the city, if there's clouds, if there's snow, well, not in Thailand, but So many data, and you cannot call BMW and say, I want to have your test data, because they will say, no, it's ours. So you have to make it by yourself. And there's a lot of process here, which I will bypass. But the whole point is that you're able to do this offline in real time. And this tool that we have. So well, you can read about that later. Time is of the essence. So basically, it looks like this, where you're able to simulate here. So here you see we're simulating this car, and these are the sensors around the car. So you see that when the car is moving near the column, we see the column coming on the other way to see what's happening. So these are all sensors, because you have radar, you have, here I was talking to you about maps. When you do simulation like this, you have front camera, back camera, you have radar data, you have LiDAR data. All this can be simulated. We have tools to do it, but you need to work very hard to make many cases. I'm telling you now, if somebody in this room is able to make a package of 100 million cases, you will call a car company, they will buy it right now. So these are versions of maps that can be, of course, changed, and tools on how to do it. Just one last thing, I know times is of the essence here, but all the models that we have, just keep in mind that ADAS is not only for vehicle. We have customers using this for trucks, tractors, military vehicles. So it could be an ADAS for a drone. It could be an ADAS for agriculture in a farm. Instead of having a driver in the farm, you know the tractor's working alone. So there's many applications. In the US, John Deere is a big maker of farming equipment. They're using our tool for making ADAS. So they have tractors, they have many farming equipment working alone, working with Renault also doing this. And Flanders Make is a French company. They're using it also on tractor to, you know, in the highway when you want to cut the grass, this is a robot, autonomous driving. So that's it. These are the things. If you have questions, I'm here, or our friends from PTS are there. Kapun Kap. Thank you very much.